So, at the end of the last video, we recognized that we had a need for some way to get this client entity to move as soon as the player presses the D key. So how we had it set up in the last video is as soon as you press the D key, you get this input sent out, and then we have to wait for the server to process it and send a response back before we're able to actually tell where we should be. So we were waiting for our authoritative state from the server before making any changes on the client side. We can't do that anymore. We need to make changes on the client side as soon as the key is pressed. So, what changes do we want to make? Well, we want to end up in a state that agrees with what the server is going to tell us, right? We want to end up at 1-0. And we're starting at 0-0, just like the server had us. So the server did its processing. It had us at 0-0. It processed one movement iteration using this input of moving to the right, and that's how it got us to 1-0. We want to do the same thing over on this side. So we want to start at 0-0, and we want to copy exactly this movement that the server did. We can ignore the input change because we already accepted inputs on the client side, and we can ignore the sending step because we don't need to do that. But we do need to do the movement. So here, we need to process movement just like the server did. And in an actual implementation, this will end up just being shared code. So you'll have a shared library that has your movement processing code, and you'll feed it the initial state of an entity, and it'll move that entity. So we know that this movement processing will be exactly the same on both sides as long as we start in the same place, which in this case we should be because they started in the same place in our example and we are using the same input on both sides. So if we start at 0-0 and we process this movement using the same logic as we did in the last video, we would end at 1-0. Right? So this is us predicting where the client entity is going to end up after the server's done processing and it sends us back the authoritative state. So predictions are no good. If you're always predicting, you need to reconcile with the authoritative state at some point. So in this case, we would reconcile just by comparing where we ended up. So here we ended up at 1-0. The authoritative state is 1-0, so we're good. We predicted correctly. If we didn't predict correctly, we would have to figure out why the misprediction occurred and reconcile our local state somehow so that we accept the authoritative state and deal with things in different ways. But we'll get to that towards the end of this. Right now, the only issue that we have is we're only processing one movement tick between this input being sent and the state being received. So everything's working as long as that is true. But that'll probably only ever be true on LAN, and even then, probably it won't be the case depending on your setup. More likely, this will be something more like this, where you send the inputs and you have multiple ticks that occur before you receive the state back from the server. So in that case, where do we end up? Well, let me make this a little bit wider. There we go. So first movement, we ended up at 1-0. Then if we move again, holding down the same input, we end up at 2-0, and then 3-0 on the third tick. So if we try to go through the same process that we just did using this data, we would end up comparing and seeing we're currently at 3-0, but the authoritative state says we should be at 1-0. And that's an issue, because on the client side, even though I wrote these things out and we can see them here that, oh yeah, you were at 1, 0 back here, so that's fine. We have no programmatic way of saying back in time, we were at 1, 0. And that point in time when we were at 1, 0 corresponds to this point in time that you're talking about in this input state message or in this position message. And comparing those and seeing that they're the same thing. We need some way of going back in time on the client side and comparing to see if we actually predicted correctly. So for that, we need two things. One of them is we need an actual concrete concept of time, right? We could try to use wall time. So we could try to say this thing occurred at 4:01 p.m. You could do something nuts like that. And you could go down to a second or a millisecond level. But that's not too useful for us. And the reason why it's not useful is we have a distributed system. We have a client, we have a server, and we have other clients. And across all the participants in this system, our clocks aren't going to be synced. So locally, if we appeal to a wall time, that's fine, but we won't be able to compare our wall time to the wall time of any other participant in the system. What I mean by that is if the server processed its movement and then sent an updated state and included its local time for that, well, it wouldn't be useful to us on this side. We couldn't look at that local time and determine anything based on it because there's nothing syncing the two sides. So this isn't useful. But we do have something that we've been talking about a little bit that does give us a strong concept of time. The thing we've been talking about is a tick. And you're all smart, so you probably already understand what tick means in different contexts. But I'll just make it very clear here what we're talking about. In one context, a tick is the actual tick function, specifically the tick function of the simulation. So it's a function that's being called every so odd milliseconds. In the case of our implementation, it would be every 1/30th of a second. This tick function will be called. And that is the function that's calling all of these simulations systems. So when we talk about something like a movement system being called or an input system being called, those are happening once every tick. So that's one concept of tick. The other context where we use the word tick is in talking about which iteration of the simulation's tick we're on. So it's the iteration number of the simulation's tick. So if we've called the simulation tick 40 times, then we're on tick 40. And hopefully that makes sense, because we're going to use that second definition, the iteration number of the tick, as our concept of time. So anytime we do anything, like when we want to change these inputs, we have to say what tick this request is for. When do we want those inputs to be changed? So just for this example, I'm going to throw some numbers around. I'm going to say we're requesting these inputs be changed to the right input being active on tick 20, right? So in this example, I'm saying tick 19 happened somewhere up here. We pressed the D key between tick 19 and tick 20, and then all of this movement processing is happening on tick 20 and tick 21 and tick 22. So that's all this stuff. This message corresponds to tick 20. Yeah, let's just make it clear this movement is for tick 20. All right, so now we have an actual concept of time. We have something to work with here. But time isn't useful in the distributed system by itself because we still have that issue of it being a distributed system and there needing to be some type of sync that gives us a relationship. Like we have some sort of weak relationship here where we sent this, we said we wanted to update this on tick 20, and this server received it and processed it on tick 20, but we don't actually know that that will work out, right? Like what if client's behind the server? What if client is on tick 18 and it makes a request to process this on tick 18, but the server has already processed tick 18? Well, the server will get the message for the tick that it already processed and will have to drop it. So there's synchronization that has to occur between the client and the server, but that's going to be the topic of the next video. So for now, we're just going to make an assumption that the client is always ahead of the server, such that when the server receives this message, or this message rather, it'll receive it early enough that it'll be able to process it and it'll be totally fine. So that's a bit of an aside, but all of that is just to say we now have a concept of time and we have a relationship between the client and the server that allows us to use that time. So we have time. The other thing we need is a history. We need a thing that'll tell us where were we at different points in time. We're going to use an input history and not a position history. So the input history we're going to use, I'm going to get rid of this scenario down here, start using up the space. So we're going to use an input history like this. And the reason is it's more convenient for us to use inputs instead of positions because inputs give us all we need while being smaller, fewer bytes to send across the wire. And we know that because our systems are deterministic, if we have a starting state, so say we have our position of 1, 0, and we have a given input, we can always recreate what came after that state. It's deterministic. It will always occur the same way. So we get to save some time or save some space by having an input history. And processing-wise, when you actually go to build out the implementation, it's less code to maintain. There's less lerping and everything that has to happen if you just have all the inputs and you're not trying to move between positions all the time. So it makes things just cleaner. The other thing is, like I talked about in the last video, the client's already talking in terms of inputs, right? The server can't trust any positions coming from the client. So it's easier to just stay talking about inputs all the time, and on the client side, build an input history instead of a position history. There are plenty of engines that do use positions, though. If you use positions instead of inputs, normally you call it a snapshot. So you have a snapshot of where every entity is at a point in time. Something like the source engine will use that. But the specifics of that are more advanced in this video. So hopefully my explanation of why we're using inputs is sufficient. I'm trying to explain it in a minute when it really could be like a 30-minute video by itself. But accept what I have told you. We are going to use inputs. So we have our history and we have our time. Cool. We have everything we need now. And what we need to do next is the second part of this. We did our prediction. Now we're trying to do our full reconciliation between our local state and this update that we've gotten from our server. What goes into that, right? So just take it back for a second. Where are we at? Well, we sent this input. The input was processed. While it was being processed, we predicted. We got something back. And now we're trying to line up that thing that we got back with this point in time, because we now have that time. We have the tick 20 to line it up with. And we're trying to see, did we predict correctly or did we mispredict? And we're trying to see if we predicted or if we mispredicted, what caused the misprediction and how do we reconcile our local state with the authoritative state. So that whole process to solve those problems is called server update reconciliation, and it has a few steps. So step 1 in update reconciliation is to apply the authoritative data that we have. So we received this message back from the server that said that we're at position 10. We would just apply that first off. So apply the authoritative data. So the example is going to be right here. And we're going to say we start at 00, and locally we move to 10, 20, and 30. But these are all predictions. So that's where we start at. We did our predictions. This is our local state. And I'm going to move down a little bit to give us more room. So that's our local state. And then we received the update. So let's say update received right here. So now we're applying our reconciliation steps. So first step, we're going to apply the authoritative data. So we're going to move from 30, which was our predicted position, to 10. All right. Something I'm not going to list here, but that 30, before we overwrote it, we just set it off to the side. We would save it somewhere so we know originally you were at 30 because we're going to be using that for comparison later. So we've applied this authoritative data. Now, step 2 is we're going to replay any inputs that occurred after the tick that the authoritative state refers to. So we're going to replay any inputs made after the authoritative data. Right? So still pretty simple here. Tick 20 is what this 10 corresponds with. We have state in our history from tick 21 and 22. So we're able to just apply that directly. So 20 is another prediction. 30 is another prediction. So like I mentioned, where we saved this before we overwrote it, since we have that off to the side, we can compare. Originally we were at 30. We went through applying the authoritative data and replaying our input history, and we ended up at 30. So that means we correctly predicted the update that was going to occur. And because we correctly predicted, everything is really nice because we don't need to change anything. All of this that we did means any other changes that occurred are all fine. So one change that could have occurred is visually we could have been moving somewhere, like we could have had a render system that was lerping us between two known positions. And wherever it has us right now, it's totally cool. We don't need to move anywhere. Right? So that's really nice. But what happens when it's not nice? What happens when a misprediction occurs? So if we mispredicted, we need to reconcile the local state with the authoritative state. And what that looks like differs a lot depending on what the potential causes of misprediction are in your particular setup. Right? So what would a misprediction look like? Let's say we received an update and it was for 10-0 instead of 1-0. Well, applying our inputs would put us at 11-0 and 12-0. And we'd do our comparison and we'd see we're not in the correct spot. We mispredicted. Well, in order to reconcile our local state with the new authoritative plus predicted state, we would need to do something, and that something depends on why did we mispredict. So if you're using UDP, maybe you dropped a message. So you sent out an input request and you predicted that it was going to be applied, but the server never got it. Well, in that case, in order to reconcile your local state, you need to move yourself back to wherever the server thinks you are. But that's kind of fine because the steps that we went through, we applied the authoritative data first, and then we replayed any inputs. So we can just go back and apply the authoritative data, and it's fine. The only other reconciliation you might have to do is this input history. You might have to change it because it's likely that in your server implementation, you might have some way of detecting, like, this player hasn't responded in a while, like detecting that messages were dropped. Maybe you have a heartbeat going on. That's expected at TCP level. So if the server detects that messages were dropped, maybe it stopped moving the player entity, which is a nice thing for a server to do. Because if you start dropping messages, but the server doesn't stop you from moving, then you can run off a cliff really easily. So the server might have done some processing to say a message was dropped, so we're going to stop you. And if that's the case, then these inputs that we predicted would have to be changed, right? Because maybe on the server side, tick 21 and tick 22 were actually zeroed out. So that's one example, but how you actually reconcile the local state with what you get back from the server depends entirely on what the causes of misprediction are. But that's it. So client-side prediction and server update reconciliation, that's all the steps. We went through and predicted what the server was going to do. We received the authoritative state, and we went through the examples of what happens if you correctly predicted and what happens if you incorrectly predicted. And the pieces of information that we needed in order to accomplish this were just a concept of time and an input history. So pretty simple here. We're still not too bad as far as networking implementation and theory goes. We did handwave something though, and it was the relationship between the client and the server, how the synchronization works that allows us to take advantage of these ticks going back and forth and know that the experience will be somewhat consistently nice. So the next video, we're going to thoroughly go through the synchronization process. And I'll give you a little bit of a forewarning that it's going to start to get more brain bending. Like we're going to be talking about how time differs between the client and the server and how they're in different frames of reference and all that. So it's fun, it's cool stuff, but buckle down a little bit. You might have to watch the video a couple times. Might take a little bit to wrap your head around it. So all that stuff is perfectly normal. Don't worry about it if it feels like it's starting to get more confusing as we go along. So next video is client-server synchronization, and I will see you there.